Welcome to The Explainer. Today, we are breaking down three concepts that literally run the universe: work, energy, and power. And trust me, once you get these, you'll see the physics behind, well, everything, from launching a rocket to just dragging yourself out of bed in the morning.
But let's kick things off with a little puzzle. Imagine you're pushing against a brick wall. You're giving it everything you've got. You're sweating, your muscles are screaming, but according to a physicist, you've done exactly zero work. How on earth is that possible? Well, stick around, because the answer is going to completely reframe how you think about all this stuff.
Okay, so let's crack that wall puzzle. First up is work. And the first thing we have to do is kind of forget what we think work means in everyday life and start thinking like a physicist.
Normally we'd say studying for an exam or even just holding a heavy bag of groceries is hard work. And yet, feels like it, but in physics, the definition is super strict. For work to be done, a force has to actually make something move. If there's no movement, no displacement, there's no work. So all that effort against the wall? Since the wall didn't budge, from a physics point of view, no work was done. Simple as that.
And here is the formula that puts it all together. Work equals force times displacement. But check out that last little bit, cosine theta. Now, theta is just the angle between the direction you're pushing and the direction the object actually moves. And believe me, that little detail, it changes everything.
Let's start with the easy one. You push a shopping cart forward and it moves forward. Your force and its movement are going in the exact same direction. The angle is zero. We call this positive work. You're basically adding energy to the cart, making it go.
Okay, now for a classic physics brain teaser. You pick up a heavy suitcase. To hold it up, you're applying a force upwards, right? Fighting against gravity. But you're walking forwards, so your force is vertical, but the movement is horizontal. That's a 90-degree angle. And the cosine of 90 degrees is zero. So, as weird as it sounds, while you're walking, you're technically doing zero work on the suitcase. Your arm might disagree, but physics is clear.
And yep, work can even be negative. This is when the force you're looking at is fighting against the direction of motion. Friction is the perfect example. A puck is sliding across the ice, moving forward, but the force of friction is pulling it backward, trying to stop it. In this case, friction is doing negative work. It's literally stealing energy away from the puck.
So, if work happens when a force makes something move, what's being transferred in that process? Well, that brings us to our next huge concept, energy. The best way to think about energy is as the official currency of the universe. You can't do anything without it. At its core, energy is just the capacity to do work. If something has energy, it has the potential to make something else move. And it's no coincidence that work and energy are measured in the same unit, the joule. They're two sides of the same coin. Now, for our purposes, energy comes in two main flavors. You've got potential energy, which is basically stored energy, just waiting to be used. Think of a stretched rubber band or a book sitting on a high shelf. And then you have kinetic energy. This is the energy of motion. That same book, but now it's falling. And here's where it all clicks into place. The work-energy theorem. It sounds fancy, but it's actually super simple. The amount of work you do on something equals the change in its kinetic energy. So when you push a car to get it started, the work you put in with your muscles gets directly converted into the car's energy of motion. It is a perfect one-to-one trade. So we have work, which is making things move, and energy, which is the ability to do that work. But there's one more piece to the puzzle. Because it doesn't just matter that you do the work, it also matters how fast you do it. And that, my friends, is power.
Think about this for a second. Let's say you have two cranes. They both lift the exact same car to the exact same height. So they both do the exact same amount of work. But one crane does it in 5 seconds, and the other zips it up there in just 2 seconds. Which crane is more powerful?
Well, the faster one, of course. Power is all about the rate of doing work. It's about how much energy you can transfer in a certain amount of time. If you do the same job in half the time, you are twice as powerful. The unit we use for power is the watt. And you see this idea of power everywhere. A 100-watt light bulb is using 100 joules of energy every single second. A car engine's power is rated in horsepower, which is just another unit for watts. Or just think about a kitchen blender. A cheap one might be 300 watts, but a high-end one that can turn ice into snow in a few seconds, that could be over 1,000 watts. More watts means more power, which means it gets the job done faster. Now, we've been talking a lot about mechanical energy, pushing and pulling and things moving. But that's just one type. Energy is a master of disguise, and the really cool part is watching it change from one form into another. A hydroelectric dam is just a fantastic example of this. You start with all that water held back by the dam. That's a massive amount of stored gravitational potential energy. Then they open the gates, and that potential energy turns into kinetic energy as the water rushes down. That moving water spins a giant turbine. Now we have rotational energy, which finally drives a generator to create the electrical energy that powers our homes. It's this incredible chain reaction of energy transformation.
All of these transformations, from potential to kinetic, from mechanical to electrical, they aren't random. They're all governed by one of the most important, most fundamental laws in all of physics. You could call it energy's golden rule.
It's the law of conservation of energy, and it's a beautifully simple idea. You can't make energy out of thin air, and you can't make it disappear. The total amount of energy in the universe is constant. It's always been the same. It just changes form.
Let's go back to that falling ball to see this in action. Okay, so imagine holding a ball way up high. Right before you let go, it's not moving, so it has zero kinetic energy. 100% of its energy is stored up as potential energy. Now, you let it go. As it falls, it loses height, so its potential energy goes down. But it's picking up speed, so its kinetic energy goes up. And right at the halfway point, it's a perfect 50-50 split. Half potential, half kinetic. But notice, the total amount of energy is exactly the same as when it started. And then, in that split second, right before it hits the ground, it's at its lowest point and moving its fastest. Almost all of that original potential energy has been converted into pure kinetic energy. The form has totally changed, but the total amount has been perfectly conserved the whole way down.
So let's wrap this up. Work is a force causing movement. Energy is the capacity to do that work, and power is how fast you get it done. But the big takeaway, the golden rule, is that energy is never lost, it just changes its clothes. Which leaves us with one last question to think about. When a bouncing ball finally comes to a stop, where did all its energy go? Well, it was converted into other forms, like the sound of the bounce and a little bit of heat from the impact. The energy is still out there, it's just been scattered. It's become less useful. And that idea, that energy tends to spread out and become disorganized, well, that's a whole other can of worms called entropy. A little something to chew on for next time.